Welcome back. Well, it's useful to understand what happens in collisions, particularly what happens to the kinetic energy. So I'm going to consider the kinetic energy, first of all, in an elastic collision. An elastic collision. So conceptually, intuitively, you can think of an elastic collision as one that bounces very well. All right, well, we'll get to that in more specific detail. But during any interaction between two objects, when one object hits another, the force of 1 on 2 equals the negative of the force of object 2 and object 1. So that's just Newton's third law expressed. And it never is violated. Now, a collision between two masses, which whether, it doesn't matter what the nature of the collision is, this will hold true. But if in particular it's an elastic collision, then the work net, the net work done during the entire collision, is 0. And you know that from the work energy theorem, total work is delta K. So if the work net is 0, then there is no change in kinetic energy. Total before is total after. So that's the fundamental idea of an elastic collision. Now, if on the other hand there's a loss in the total K, the total kinetic energy goes down, then negative net work must have been done, and vice versa. Let's do an example, or let's consider conceptually an example here. Hopefully this isn't too hard to visualize without seeing the objects themselves. We're going to have a goat that butts a pig. So you got that in your mind. You might think, why would that happen? Well, because you happen to be visiting your relative's farm and they have goats and pigs. And goats, I can tell you from personal experience, they like to butt into things. I've had a friend that had goats, and I'd go to my friend's house, and these goats would look at me and put their horns down and come charging. And I'd grab the horns and slam them onto the ground. No animals were hurt in the aforementioned activity. Okay, moving on. The pig is at rest. The goat butts into the pig. Now you can kind of visualize that happening. The horns of the goat push into the side of the pig and compress the pig a little bit, right? The force of interaction is F. We'll just call it F. Now, during the collision, the goat that is doing the butting, so to speak, moves D1 because deforming the pig's body a little bit pushes his head into the side of the pig, say. The pig moves D2. Now, those don't have to be the same because they're not rigid objects. They are, well, the pig has a certain amount of malleability, so to speak, so his body can be altered in its shape, and the whole center mass of the pig doesn't have to move the same distance D2 that the goat moved, the center mass of the goat moved, which is D1. In other words, the goat and the pig are merging. Yes, they are merging together. Their center masses are coming closer together even after they begin to collide. Okay, now, work done on the goat. The goat is, say, pushing to the right, well, moving to the right, but the force on the goat is from the pig, which is then to the left. So the goat gets negative work done on it, and that work done on the goat is negative because the force on the goat is to the left, the displacement is to the right, and so it's minus F D1. D1 is the distance the goat moves. Positive work done on the pig. Yes, it has positive work because the goat force is to the right and the pig moves to the right as well. Maybe not the same amount, but it would be positive FD2. All right. Now, does D1 and D2 have to be the same? I already said it doesn't. So let's say D1 is greater than D2. So that means the goat is moving further than the pig moves. Then what's happening to total kinetic energy? Well, this is negative work, this is positive work, and that directly relates to what's happening to total kinetic energy. The negative work is greater because D1 is greater. The positive work is less, so total kinetic energy is decreasing. If D1 is less than D2, then total K is increasing by the same token. K goes down, K goes up. Now we're going to define delta S. Basically, that's the change in the separation between the goat and the pig. Well, if you think about it, it's just the distance that the pig moves minus the distance that the goat moves. If you take the difference, you have the change in the separation, how much the separation altered. If it's negative, it means they're getting closer together. If it's positive, they're getting further apart. So then what's the equation for the change in the total K? Well, based on what we have here in logic, the total kinetic energy will change according to what the total work looks like. If it's negative total work or positive total work, it will decrease or increase respectively. So it's force times D2 minus D1. Basically, that's combining these two things together. And we can call that now F delta S. So if delta S is negative, meaning they're coming closer together, then the force times that negative quantity also expresses how much the kinetic energy has reduced. And if it's positive, they're getting further apart, times F, then the total kinetic energy is increasing. So now we're going to look at colliding carts and consider how this works in a particular situation.